Sorry, I meant to record from the beginning because people, not everyone in this era of COVID is in the United States. Some people are in other countries, and they need to have access to a video to be able to watch. So sorry that I meant to auto record. I didn't. I'll start doing that from the second lecture. But for those of you who are online looking at this, maybe I'll just make sure that you have this up. There's a website, there's an email address to email me for the course, grading, etc. This is all online. The grading syllabus is online. The grading method is online, etc. The breakdown of grades. Filling out the Google form. I guess the Google form link is only in the Zoom chat. So if you're watching this on YouTube later or whatever, wherever I put it, then email me for the Google form URL if you haven't already filled it out. Okay. Okay, great. So let's get started with some scientific content or some CS here. So we're going to start off with streaming. And just so we're all on the same page, I want to do a really, really simple streaming algorithm, right? So that it's not completely abstract, which is, example, there's let's say a sequence of, sales, and I want to know, the gross sales amount in dollars, for today. Right, so my data set is basically this database of a bunch of transactions, a bunch of sales that happened today. Maybe there are a million sales today. I only want to know query this one thing, which is what was the gross money that I brought in from my sales. This has a very trivial solution, which is just keep a counter, right? It starts at 0. Every time there's a sale, I add in the amount. So that is a streaming algorithm. Okay, so just to give you something concrete. Okay, it's not so. This is so easy. Easy solution. Just keep a running sum. And how about, let's say the number of transactions, the number of sales, not the total amount, but just how many people bought stuff. Also easy, right? Keep a counter. And if there were a total of n transactions, my counter will have only log n bits, right? So, the first problem I want to look at is exactly actually this problem, which is just keeping a counter. And I want to show you that actually even there already there's something non-trivial. You can actually do better. Okay. If you define the problem, if you relax the problem a little bit, which we'll see. So approximate counting. Basically, we have so we want to maintain a counter n. Subject to 3 operations. So this is a data structural problem. So one is init, which just sets the counter to 0. There's increment, which increments the counter, and there's query, which just returns the number, right? Returns, let's say, some approximation to the number, to the counter. Okay. Now, if you wanted an exact algorithm for this problem, then it's not too hard to prove that it's impossible to store. If all I tell you is that the number is guaranteed to be between 0 and t, then it's not hard to prove that you need log t bits, okay, of memory to be able to solve this problem. Why? Because if you're using less than log t bits, then, just by the pigeonhole principle, there are two different numbers, there are two different increment amounts that would land your data structure in the same memory configuration. So from the perspective, so let's say those two amounts are, A and B. So if you do A increments, you'll be in memory, your memory configuration will look like blah. If you do B increments, it'll also look like blah. It'll look exactly the same. So from the perspective of your data structure, there's no difference. So it's going to return the same output for both A and B. But of course, at least one of those has to be wrong because A and B are not the same number, right? So there's no way to solve the problem in less than logarithmic memory if you want a deterministic exact solution. So we're going to settle for an approximate solution where I don't necessarily want the exact value of the counter, but I'm happy to have it to within, say, 1% error. Okay. And I'm not going to show it right now, but it turns out that even that is too strong and is impossible in logarithmic memory. But so we're going to add one more level of relaxation, which is not only am I willing to allow for 1% error, I'm also willing to allow for a randomized algorithm that has some probability of outputting the wrong answer. 1%, with 1% probability, my answer will not be within 1% of the truth. Okay. So good. So now what's the best kind of space bound I could hope for? So from a deterministic algorithm, I said that it's impossible to have a deterministic algorithm with low memory, but let's say we didn't know that yet. What's the best I could hope to have in terms of memory consumption? So if I want to know the right answer, what's the best memory that I can hope to achieve? Let's say that I'm promised that, n is between some 0 and t at query time. Well, let's just look at the powers of one. So if I need to have the right answer to within 1% error, let's look at the powers of 1.01 all the way up to t. So, okay, so there's 0, n could be 0, or it could be 1, or it could be, something that's close to 1.01 or 1.01 squared, 1.01 cubed, 1.01 to basically the log base 1.01 of t. So these are all, other than 0, these are all the different powers of 1.01 that are between 1 and t, right? And my true value of n is somewhere in this like line. So this is 0 and this is t. So I know the true value is somewhere here. So let's say it's here. Then it's enough for me to round it to the closest, power of 1.01 that's near it. I could round to this one. So this is a silly example because 1.01 cubed is just roughly 1.03, which is approximately 1. But, n could be somewhere in the middle of this line. I'll round it to the nearest power of 1.01. And by that rounding, I'm only losing 1% of the value, right? So that would be a valid answer. So, in principle, I just need to, as long as my memory state is storing the closest power of 1.01 near my value, then that's good enough, right? So how many powers of 1.01 are there up to t? Well, that's this, log base 1.01 of t. So the number of bits of memory I need, so to remember a number up to an integer up to, let's say, log base 1.01t, I only need O of the logarithm of that number of bits. Right? And so I said log of the logarithm base 1.01 of t bits. Right, and just remember, this thing is the same as, log base a of b is the same thing as log b over log a. So this is the log of log t over log of, I'll call it 1 plus 0.01. And another thing to remember is that basically by Taylor expansion, the log of 1 plus epsilon is roughly epsilon. So this is basically log, or roughly log of log t divided by 0.01, which is log t plus log of 100, right? Or more generally, if instead of 1.01, if it had been 1 plus epsilon, if I just said 1 plus epsilon, this would have been 1 over epsilon. Okay. So that's kind of maybe the best that's something I could strive to achieve in terms of my memory consumption, like log n plus log 1 over epsilon bits to store this counter n. Okay. And that's what we're going to in fact achieve. There's going to be another extra term because it's a randomized algorithm. There's going to be a dependence in the memory on the failure probability as well. Okay. And I guess another thing I want to argue too is that not only is this like that actually I can't really hope to achieve much better than this. And the reason for that is, if I look again at this picture, these powers of 1.01, let's look at, this value. Let me use red again. Let's look at this value and then this value, and then just like skip to every third one. So skip this, go to this value, skip this, go to this value. Okay. I also claim that kind of the memory configurations, if n had been this value here, versus if n had been this value, versus if n had been this value, etc., the memory configurations of the data structure had better be different for those, because there is no number that's both a good 1% approximation, it has 1% error for one number and also has 1% error for the other number. Okay. So they need different memory configurations so that I can tell them apart, which means that, my memory has to be basically, at least something like log of, I need memory to be at least log of something like, log base 1 plus epsilon of t over 3, because I skipped every third one. But that's omega of log base log 1 plus epsilon t, right? So really, we're going to try to achieve this, but we also can't really hope to achieve much better than this by some additive constant. So before now I show you how to do it and where this is, and who did it. Are there any questions about anything I've talked about so far?
Oh, so if you're proving this lower bound of log t, then that's just sort of like you're going to try to keep the magnitude or something?
Yeah, basically I basically want to keep track of the logarithm of the number.
Yeah. Okay.
The logarithm base 1 plus epsilon. And by the way, I do see now, one thing that I'll say is if you have a question, unfortunately, I don't know if it's my version of Zoom or whatever. I actually don't get notified when people type in the chat. So I'm only seeing now that there have been many questions typed in the chat. If you have a question, do feel free to just unmute yourself and say question, and then I'll know that you have a question. Because I won't, unfortunately, I might not see it if you just put it in the chat. So I see there's a question about, is the class only 1 unit? I believe it's, I don't know the answer to that. I believe it's not 1 unit. I mean, it should be a number of units which is comparable to a regular course. But I can check on that. And apparently, so 294s in general, there are lots of classes that are 294s. 294s are basically just special topics graduate courses. I guess each one has a different number of units. So my 294, which is 294-165, should have more than one unit. If it doesn't, then I need to talk to someone in the registrar and make sure that's fixed. But if it only says one unit, that's a bug. Any other questions about the course or about the stuff I just said for this approximate counting problem?
Yeah.
So do you want to?
So now that I am paying attention, maybe if you have a question, raise your hand in the Zoom, and then I'll go in that order. Okay, so Serena.
Yeah. So you mentioned that this algorithm is, or that you expect this to be wrong, like some proportion of the time, but I'm not seeing where that could happen. Like it seems like it will be within some. Yeah.
Yeah. So good. So I haven't shown you the algorithm yet. So what I showed was just kind of a, going into trying to design the algorithm, what's the best that we can hope for, or what's something that we can reasonably hope for. Notice that this business of rounding to the closest power of 1.01 is not a valid streaming algorithm because, the problem is I don't know n. In order to round it to the nearest power of 1.01, I need to know what n is, right? But I never am given n up front. All I'm told is like init, now I know n is 0, and then I'm told increment, some number of times, right? And every time an increment happens, I need to make a decision as to how to update my memory state. So if I'm trying to keep track of the logarithm base 1.01 of n, that's a real number. That's not an integer. So if I'm trying to keep track of like rounding it to the closest integer, how do I decide, when to increment my value that I'm storing, right? So like, for example, let's say that I'm trying to just keep track of log base 2 of the number, right? So let's say the number right now is 5. Okay, n is 5. In my memory, what I'm storing is log base 2 of that, which is 2. So I'm storing 2. And then now someone says increment. So n now is 6. But I don't know that it's 6, right? All I know is I'm storing 2. So they said increment. Should I increment my 2 to 3? Or should I stay at 2? It's not obvious what to do, right? And then they say increment again. Now n is 7. Okay. Again, all I'm storing is 2. Do I increment at this point or not? Right. And what we're going to see is like the way around this that gives good results is to probabilistically increment. So whenever I'm storing a value, and someone says increment, I'm going to increment with some probability and stay where I am with some probability. And that's where the probability is going to come into this.
I see. Okay, that makes sense.
And I saw there was a question by Robert. Do you still have that question?
Oh, yeah. I think I was just going to ask if you could explain why we know you can't do better than like an additive factor better than this again.
Oh, then the log n plus log 1 over epsilon?
Yeah.
So, I mean, maybe let's just say it with powers of, let's say I need to be within a factor of 2 of the right answer, right?
Uh-huh.
So if you look at the powers of 2, 1, 2, 4, 8, 16, 32, 64, etc. Okay, all I'm saying is, look, so let's circle some of these numbers. 1, 8, 8 is a good one, 64, and then let's do one more, 512. Okay, these numbers that I've circled or boxed are values that n could take in principle, right?
Yeah.
And my claim is that whatever let's say we had a deterministic data structure.
Mm-hmm.
Let's look at its memory footprint. Its memory footprint is just like a bunch of bits, right? It's just a bit string. And what I claim is that memory footprint had better be different for 1. If n is 1 versus if n is 8, it had better
I see.
Storing something different. Why?
Right.
Because its answer for 1, if it's storing the same thing for 1 and 8, its answer for 1 and 8 will be the same.
Mm-hmm. Right, yeah.
But there is no number that's both within a factor of 2 of 1 and 8.
I see, yeah.
There is no number that's both within a factor of 2 of 8 and 512. All these numbers had better have different memory states.
Right, okay, that makes sense.
Yeah, so that means that, in particular, in this example, I need at least 4 different memory states for these 4 box numbers, which implies I need at least log 4 bits of memory, right?
Right.
So that's all I was saying.
I see. Okay.
And that basically will give you a lower bound that looks like this.
Okay.
Okay. Any final questions before I continue? Okay, Iman?
Sorry, is that a 3 underneath log 1 plus epsilon of t?
Yes, it is.
Okay.
And it's because I boxed every, should it have been 3, I think? Yeah, because I boxed every third element, so.
Okay. And then I had a very quick question. If we're enrolled, we don't have to fill out the form, do we?
If you are already enrolled in the course, you do not have to fill out the form.
Okay.
Okay,
Thanks.
great. Okay, so good. It looks like no one else is raising their hand. Let's continue for now. So the history here is basically Rob Morris. There are 2 Rob Morrises. There's the father and the son. So the son is a faculty member at MIT and EECS there. He does systems. His father was also a computer scientist who at some point worked at the NSA. I think he was like chief scientist at the NSA, and then also worked at Bell Labs. He was a researcher at Bell Labs. And there's a nice article on this by, his name is Jeremy Lombroso. I'm probably saying his name wrong. So see article on archive by Lombroso. And this was in 2018. It's a historic. So he's at Princeton in the CS department, but it's not a scientific article. It's a historical article where he talks about the history of like where these algorithms came from and why they were being developed. So it's a pretty interesting read. Take a look if you'd like. So basically what he said in that article is, why did anyone want an approximate counter? Log n is already quite a small number, right? For any, for most values of n that you'll run into. Why is it so important that you can store it in log n bits? And this was in the 70s. It was, I think, 1978. And apparently there was a spell checker program in Unix called Typo. And the way that it kind of flagged whether it wanted to suggest that some word has a spelling error was it kind of looked at trigrams, so sequence of 3 letters at a time, and counted like all trigrams. And rare ones, I guess, fed into some statistics calculation it was doing to flag something as potentially a typo. If you're typing a trigram that's very uncommon, then maybe it's a typo. And I guess he didn't have enough memory in those 1978 machines to store counters for all possible trigrams. So he needed to squeeze as much, storage power as he could with his machine. So he devised the scheme. I've actually implemented this myself. And let me just pull something to show you. So this is not, let me share from my laptop. So people can see this, I hope, I think. Good. Yes. So this is doing on the order of 1 million increments. So n got to be as big as 1 million. 1 million is about 20 bits, right? And what we said here was let's try and store this 20-bit number using only 17 bits. Okay, so it's only a modest savings in our memory consumption. And we did this experiment. This is an experiment I did with someone I work with, Hua Cheng Yu, who used to be a postdoc with me. And I'll get to why we did this experiment later in lecture. There's a reason why we actually did this experiment just this summer for a very particular reason. But we did the experiment 10,000 times. So remember, this is a randomized algorithm, so it makes random decisions. So 10,000 times, we fed it different randomness each time, a different random seed. And we incremented the counter, roughly 1 million times. But we only gave the counter 17 bits to do this, okay? And what you're seeing now on the x-axis is kind of the percentage of trials. Of these 10,000 trials, what percent blah? And what's blah? If you look at the y-axis, it's the relative error from a trial, okay? So the max error we ever got was about 2% error when we estimated n. So we got a really good approximation of n with 17 bits instead of 20. 100% of the time, our relative error was less than 2%. Meanwhile, if you look at, say, 60%, 60% of the time, our relative error was less than what seems to be roughly 0.3%. Okay, so that's what that x-axis means, right? So if there's a dot here, xy, if there's a dot here, xy, it means that x% of the time, our error was y% or less. There are actually two curves here. There's the orange and the blue. The blue is the Morris counter, which I'm about to explain to you, from Robert Morris in the 70s. The orange is, so maybe just a sneak preview at what I'll say later, is Hua Cheng and I actually came up with a new algorithm which we could prove a better bound for than what was known in the literature for the Morris counter. So, and our algorithm was simple enough that we thought, oh, let's like actually implement it and compare it to the Morris counter and show that it's better in practice too. But you can see the results of that in this plot. It's not better, it's not worse, it's pretty much exactly the same. So anyway, after running this code and seeing this, we actually went back and managed to prove a better bound for the Morris counter than what was known before. So I'm not going to show you that better proof of the Morris counter today, but I will tell you what the bound is. Okay. So anyway, this is something that's actually implementable. It wasn't actually too painful for us to implement this. It took less than a day to implement this, and it gives meaningful results. And we actually also did it with, like, I think instead of giving it 17 bits, what happens if you only give it like 13 bits, etc. And you get pretty decent results. So this is something that is a real algorithm. It's not just a big O, asymptotic analysis algorithm that can never be used. Okay, great. So back to math and proving things.
Ask a quick question before.
Yep.
Or in the case of analyzing these, to generate the random number, presumably there's like some kind of pseudo-random string somewhere in the machine. Would you also analyze the amount of memory it takes to do the pseudo-randomness, or?
Yeah, so good question. Like for this algorithm, I'm assuming access to perfect randomness. So if I want, I am assuming that my computer can flip an unbiased coin and get heads with probability half and tails with probability half. For this particular algorithm, I will never need to remember my previous random choices. So, where pseudo-randomness, we will talk about pseudo-randomness later in this course. In fact, in the very next lecture on Monday. There are a lot of randomized streaming and sketching algorithms where, you make a random decision at some point, and then in the future, you have to make another random decision that's like consistent with some other decision you made in the past. For example, like you have a hash function. So, at some point in the stream, you saw, the item 5, you hashed it, you got some hash value. And then later in the stream, you saw 5 again. So you hash it, you had better consistently get the same hash value that you got in the past, which means you need to remember your hash function. And if your hash function is this big random object, and I don't want to spend the memory required to store a big random object. So that's where I'm going to need to talk about pseudo-randomness. How do you design hash functions which are not totally random, because I don't want to spend the memory to store something totally random. But they're random enough that they still work for my algorithm. Okay, so we will talk about pseudorandomness in that context, but for this particular Morris algorithm, because it doesn't need to remember its random decisions, that's not an issue. But you're right that there is an issue that I do need to make sure that I have a high quality source of randomness so that the random decisions that I do make are actually uniformly random. I'm not going to, I'm just going to assume that I have that. Okay.
All right, thanks.
Any other questions? Okay. So, so he developed this algorithm initially as part of this basically spell checker, and this was in 1978. Okay. And what was the idea? The idea is, let's say I don't store n. Instead, I store a different counter, which I'll call x. When I do initialize, I'll set x to 0. And when I do increment, I don't always increment x. I increment x with some probability. So let's try the simplest thing, which is I increment x with probability of half. Okay. So half the time I increment it, and half the time I don't in expectation. Now, when I do query, I need to return what the value is. What am I going to return? Well, the natural thing to return is 2 times x, right? Because I expect x to be n over 2 because I only incremented it half the time. So if I return 2 times x, I'm expecting to get a value that's approximately n. Okay. Now, what are the pros and cons here? So the pro is I'm storing probably a smaller number. Instead of storing n, I'm storing n over 2. So storing a smaller number takes less memory, right? What are the cons? The first con is I'm only saving 1 bit, right? N versus n over 2 is just 1 bit of memory difference. And 2, there's now some variance, right? 2 times x is not it's not guaranteed to equal n. It's just something that an expectation is n. And there's some probability that this deviates. And in fact, the probability that I don't get relative error, meaning let's say I want 1% error. I mean, if I only did 1 increment, then forget it. If I only did 1 increment, I'm definitely not getting 1% error because x is either going to be 0 or 1. I either incremented it or didn't increment. When I double it, my answer is either going to be 0 or 2. But the true answer is 1. I only did 1 increment. Neither 0 nor 2 are within 1% of 1, right? So I'm basically guaranteed to not get the kind of error that I want to get. Okay. Of course, once I do enough increments, then I'll start getting relative error with good probability. But if I did a small number of increments, I won't. Okay. So we're going to fix these one at a time. And the first thing I'm going to try to fix is item 1, the fact that I'm only saving 1 bit. So let's try and save more bits, and then we'll deal with the variance issue later. So instead, I'll increment x with probability 1 over 2 to the x, otherwise do nothing. And query, I'm going to return 2 to the x minus 1. Okay. Now, why is this a reasonable thing to try? First of all, before we talk about why this might work, what's the memory consumption? Well, let's look at it like this. Once x gets to be as big as, let's say log of, is this a good number? do something like this. Yeah. Then the probability that I ever increment again is at most well, if I do a union bound, there are at most n increments remaining. Let's say n is the final value of the counter. There are most n increments remaining, and the probability that I increment in any of them is 1 over 2 to the x, which is delta over n. So this is delta. Right? So kind of with high probability, the counter will never get to be bigger than this, because once I get to this value, it's very unlikely that I'll ever increment it again. And this is basically log of log n over delta bits, which is log n plus log 1 over delta. But focus on this part. Basically, it's very unlikely that I'll ever have more than, that I'll ever need to use more than log n bits. Okay. So we are saving kind of exponentially in our memory. Instead of log n bits, we're using log n bits. Now, why should this work is the real question. So remember what I said. We increment x with probability 1 over 2 to the x. And then query, I said, we output 2 to the x minus 1. And the reason this works, claim, is that the expectation of 2 to the x is equal to n plus 1. So the thing that we're outputting to answer a query is at least an unbiased estimator of the truth. Okay. So maybe let's prove this claim. So the proof is basically by induction on the number of increments. And let xn be the value, which is a random variable, be the value of x after n increments. Then what do we know? We know that x0 is 0 with probability 1. So 2 to the x0 is in fact 1, which is 0 plus 1. It's n plus 1. So that's the base case. This is the base case. So this is an inductive proof. Now we'll show that the inductive step, that will show that the expectation, if the expectation of 2 to the xn is equal to n plus 1, that implies that the expectation of 2 to the xn plus 1 is equal to n plus 2. Does that make sense? So what do we know? The expectation of 2 to the xn plus 1 is equal to the sum over all j from 0 to infinity, the probability that xn is equal to j, times the expectation of 2 to the xn plus 1, given that xn is equal to j. Okay. And what is this? This is equal to, again, the sum j goes from 0 to infinity, the probability that xn is equal to j. What is this conditional expectation? Well, we know that with probability 1 over 2 to the j, we're going to increment, and with probability 1 minus 1 over 2 to the j, we won't increment. So with probability 1 minus 1 over 2 to the j, x will stay j. So then 2 to the xn plus 1 will just be 2 to the j still. And with probability 2 to the j, we will increment it. So we'll get, this is 1 over 2 to the j. We will increment it, and then we'll get 2 to the j plus 1. Right? So this now in here is just 2 to the j minus 1 plus 2. So this is equal to, I think, right? So 2 to the j minus 1 plus 2, which is equal to 2 to the j plus 1. So this whole summation is equal to the sum over j of the probability that xn is equal to j times 1 plus the sum j goes from 0 to infinity of the probability that xn is equal to j times 2 to the j. Now, anyone tell me, what is that?
Just one?
Yeah, that's 1, right? Just the sum of probabilities over all. If you sum over all possible values that a random variable can take, and you take the probability of each, that's just 1. Right? And what's another way of writing this? Okay.
Expectation of
2 to the xn.
Yeah, this is equal to the expectation of 2 to the xn, which by our inductive hypothesis is equal to n plus 1. So overall, this is equal to n1 plus n plus 1, which is n plus 2, which is, exactly what I wanted. So I have the base case and I have the inductive step, so I'm done. What is going on? Okay. Weird. I can't write on my... For some reason, my iPad is not letting me... My iPad seems to have frozen. Oh, here we go. Let's reopen the app. Huh. Okay. Well, good enough. We're done with that page anyway, so we can write on the next page. It's good enough. Okay, good. So we've computed the expectation. The next thing we're going to compute is the variance. So what did we say? We said that the expectation of 2 to the xn is equal to n plus 1, which is why we subtracted 1, right? Remember, if you look here, our output to query was 2 to the x minus 1. The reason we subtracted 1 is because the expectation is n plus 1. And the next thing we want to do is the variance. So actually, let me write it like this. So we have an estimator. Our estimator for n is this n tilde, I'll call it, which is 2 to the x minus 1, right? So what we showed really is that the expectation of our estimator is correct. It's unbiased. And what we also care about is the variance of our estimator. And let me not do the, it's not a very interesting calculation. It's very similar to the one you just saw. But I will include it in the notes that I put on the website. But let me just promise you that this thing is actually, the variance of n tilde is actually less than capital N squared over 2. It's possible to prove that via a very similar kind of inductive argument that will be in the notes. So now, how do I use that to get something good for my algorithm, to analyze my algorithm? I can say, look, what's the probability that my estimator deviates from the truth by more than epsilon n? And this is Chebyshev's inequality. Chebyshev's inequality says is at most the variance of the estimator over the right-hand side squared. This is Chebyshev. And I don't want to spend time on these kind of tail bounds. I'll include that in the notes again, also that I put up either today or tomorrow. Just kind of things that I'll assume that you're comfortable with. Markov's inequality, linearity of expectation, Chebyshev's inequality, and the Chernoff bound. I know that not everyone, the prereq for this course doesn't, it's CS 170 and also some comfort with probability and linear algebra. If you've taken those courses, you might not have seen the Chernoff bound, but that's okay. I mean, I'll put it in the notes. It's it's a probabilistic tail bound that tells you a bound on what's the probability that a random variable deviates by a lot from its expectation. Okay, so it's something that gives you control on that. Okay, good. And I think maybe I'll say something about it in lecture 2 in a couple minutes when we need to use it. So what is the variance? The variance here, I said, is less than n squared over 2. So that's n squared over 2 epsilon squared n squared. And then, of course, the n squareds cancel. And this is equal to 1 over 2 epsilon squared, which isn't actually all that great. Okay. If I set epsilon to be something like, maybe points, let's think of epsilon as being like maybe 0.75. Then this is equal to 1 over 2 times 3/4 squared, which at least is less than 1, I think. Is it less than 1? I think it's less than 1, yes. So, so in particular, it's 4 squared over 2 times 3 squared, which is what? 8 over 9? Okay. So with probability, so this is the probability that I fail. So I fail with probability at most 8 over 9. That's not great. That means I succeed with probability at least 1 over 9, which is about 11%. So 11% of the time, I'm guaranteed to get an answer that's at most 75% off from the truth. Okay, that doesn't sound great, but it's something, right? It's something non-trivial. I mean, if you a priori, it's not clear how to get any decent constant chance of guessing correctly. Okay, but we can, of course, do better. So I'll call this algorithm I'll call Morris. And then now let me show you a way to improve it, which is Morris plus. What I'll do is I'll run Morris, R times in parallel. Each one is making its own random decisions. This gives me estimates n tilde 1 up to n tilde r. And then I'll actually estimate n as n hat, which is the average of these. Okay. Now, notice that the expectation of n hat is, it's the expectation of 1 over r times the sum of ni tilde, I goes from 1 to r. By linearity of expectation, this is the same as the expectation of n1 tilde, which we know is just n. So this is still an unbiased estimator. And the variance of n hat is equal to the variance of 1 over r times that sum, which is equal to 1 over r squared times the variance of the sum. And this is a fact about variances. The variance of the sum of independent random variables is the same as the sum of the variances. So this is equal to 1 over r squared times the sum of the variances. And we know that each variance is at most n squared over 2, right? So, so we know that this is basically now less than n squared over 2r. Right? There are of them, so it cancels one of the r's. So we basically decreased our variance by a factor of r. So now Chebyshev's inequality says the probability that n hat deviates from its expectation by more than epsilon n is at most n squared over 2r epsilon squared n squared. Again, this cancels. And then now I can make sure that this is less than, let's say, some eta by picking r appropriately. So I can pick r to be at least, 1 over 2 epsilon squared eta, I guess, something like that, the ceiling of that. If I pick r to be that, then this is less than eta. Okay, so now I actually have a 1 plus epsilon approximation with probability 1 minus eta. But now notice I blew up my memory because I'm running all of these r copies in parallel. So I'm blowing up my memory basically by a factor of r. Okay, so I blew up my memory by a factor of 1 over epsilon squared times 1 over eta. So my total memory is now something like log n over epsilon squared eta, which is not as good as, remember I wanted to get log 1 over epsilon, and I also wanted to get, this dependence on eta is not great either. So I can fix this, and the way I fix this, I'll call Morris plus plus, which is I run S independent copies of Morris plus, each with eta being a third. Okay. And now each one of those, so then I get basically n hat 1, n hat s. Each of these n hats is an output of one of the Morris plus copies. And then what I'll actually output as my estimate is, let's call this now n line, which is going to be the median of all these numbers. So overall, our final output is the median of a bunch of means. And now the claim is that the probability that n hat minus the actual value of n is bigger than epsilon times n is at most kind of exponentially small in S. So C is some constant. Sorry, so not in S, but let me actually fix that. So I think that if you want to be precise, what you can get is you can get 2. Let me put a precise number here. 2e to the minus epsilon squared s over 3. So you can pick it's not going to be 3, sorry. There's some constant here. We can figure it out later. It's some constant. So you can pick s to be at least, say, there's no epsilon either, actually. Yeah. You can pick s to be at least, say, ln of c times ln of 1 over delta, or 2 over delta. And then this will be basically less than delta. So in the total memory will be r times s times log t, which is going to be something like, or log n, which is something like log n times log 1 over delta over epsilon squared, which is also not the ideal thing because I want a better dependence on epsilon. Instead of 1 over epsilon squared, I want log 1 over epsilon. But kind of why does this claim hold? And the reason is, remember, we're outputting the median. Okay. Now, the median will be a bad estimate if more than half the estimates are bad. If at least half the estimates are good, then the median will be good. Okay. But how many estimates do we expect to be bad? We expect an eta fraction of the n hat i's to be bad, meaning more than epsilon n error. Okay. And we picked eta. How did we pick eta? I said we picked eta to be a third, right? I said eta is a third. So we expect S over 3 bad estimates we need more than S over 2 bad estimates for n hat to be bad. So that's a deviation. That's a deviation from the expectation of at least S over 6. From the expectation, from the expected number of bad copies. Okay. And this is exactly the setup of the Chernoff bound. So, for those of you who haven't seen the Chernoff bound yet, I will say something about it. So Chernoff basically says, say that you have x1 up to like xs are independent random variables in each of the range 0, 1. Then the probability that the sum of the random variables xi, I goes from 1 to s, deviates from the expectation of the sum by more than epsilon, let's call this mu is the expectation, by more than epsilon mu is less than 2e to the minus epsilon squared mu over 3 for epsilon in the range from 0 to 1. Okay. So basically for us, you can think that xi, so for our situation, xi is kind of 1 if n hat I was a bad estimate. It had too much error. And 0 otherwise. Right? So the sum of the xi is the number of estimates that were bad. What is the expectation of the sum of the xi? It's at most s over 3 because we set eta to be a third. So we only expect s over 3. We only expect the sum to be s over 3. What's the probability that the sum is bigger than s over 2? Well, that means it deviated from its expectation by so to go from s over 3 to s over 2, you got to deviate by s over 6, which is basically mu over 2. It's like half the expectation, right? So you got exactly this exponentially small failure probability that I was describing. That's where this comes from. This e to the minus, this behavior of kind of e to the minus s over times some constant. Okay, so that's that. And this is kind of a generic recipe for designing streaming algorithms, right? Where you first, you design some random process that describes what your algorithm is doing. You show that what you output is an unbiased estimator of the true answer. And now you get some bound on its variance. That's what we did first, right? The first thing we did was we showed that it was an unbiased estimator, and we got a bound right here on the variance. The bound on the variance was not great initially, so we improved it by averaging many copies of our algorithm. That blew up the space of the algorithm because now we have to run many copies in parallel. Okay. And then that gives us something, but our dependence on the failure probability wasn't great. So to improve that, we then took the median of many copies when each one of those copies only had constant failure probability. But when you take the median of many of them, you exponentially improve your failure probability. You exponentially make your failure probability go down. Okay, so at the end of the day, taking the median of means is getting you a space bound that looks like this. That's not what I promised you. Okay. It turns out that the right answer, so what I showed you today, we got space which looks like basically O of log n over epsilon squared times log 1 over delta. Now, it's possible to do better. In fact, Morris in his original paper already described how to do better. He didn't do this Morris plus and Morris plus plus stuff. The reason that I showed you that is it's a very generic way that basically almost always works for any problem. Okay. So it's a good thing to keep in your toolbox, this idea of median of means. And there are problems for which the median of means actually does give you an optimal result, just not this one. So what did Morris suggest that's better? So a better idea for this particular problem is the following. So what is a deterministic counter? A deterministic counter is, so one, a deterministic counter, you always increment. So you increment x with probability, I'll call it 1.0 to the x. Today, what did we do? We incremented x with probability 0.5 to the x, right? 1 over 2 to the x. So a natural thing to try is to increment with probability. Let's try to increment with probability, 0.99 to the x. Okay. So I'll ask you all. I claim that there's basically a trade-off happening here. Okay, you're trading off memory for variance. Okay. So which of these, so going from 0.5 to the x to 0.99 to the x, should that increase my memory or decrease my memory? So anyone just unmute yourself and say it. Increase, right? Because I'm incrementing it more often. So I'm storing a bigger number. So I'm probably using more memory. Meanwhile, do you think it increases or decreases the variance?
Decreases.
Decreases, right? And even without doing a calculation, that should be intuitive, because if I increment with probability 1.0 to the x, I always increment, then there's zero variance, right? Like what I'm storing is always guaranteed to be n with probability 1. There's no variance. Whereas if I increment with 0.5 to the x, we saw there was some variance. The variance of my estimator was n squared over 2, right? So a natural guess is that the variance smoothly decays as you increase the base of that exponential. And in fact, if you do the calculation, it's true. You can show that it does decrease, okay? So if you do this, you can show that incrementing with probability 1 over 1 plus a to the x works for a being something like basically epsilon squared times delta. And this leads to, if you analyze it carefully, maybe I'll make it a homework problem, it leads to memory that looks like log n plus log 1 over epsilon plus log 1 over delta bits of memory. Okay. So already this was already suggested by Morris, and it was kind of rigorously analyzed in a later paper by Flageolet a few years later. Okay. So yeah, that plot that I showed you of Morris in action, basically, you can ask, what's the optimal bound? Is this optimal? And kind of the latest and greatest bound is from June. So that's 2 months ago. Or actually, maybe it's late, maybe it's early July. So this summer is log n plus log 1 over epsilon plus log 1 over delta. So the difference is, if you didn't notice, the difference is this, right? We improve the log 1 over epsilon, log 1 over delta can in fact be log 1 over delta. Okay, and it's possible to actually prove a matching lower bound. You can prove that there is no algorithm that does better than that, up to a constant factor. To be more precise, the optimal bound is basically the min of this expression and log n. Of course, you can always achieve log n via deterministic counter. So if you tell me that, Jelani, I want my failure probability to be at most 1 over 2 to the 2 to the 2 to the 2 to the n, okay, then log 1 over delta is pretty bad. It's a pretty big number. So at that point, I'm going to be like, you know what? If you want your failure probability to be that low, I might as well just give you probability 0 of failure, and I'll give you a deterministic counter. So that turns out to be the truth. basically, this is the optimal, and also same thing with epsilon. If you want your relative error to not be 1%, but you want your relative error to be 0.00001%, then if it's small enough, I'm going to tell you, look, I might as well just give you the exact answer. So up to a certain point, kind of this is the best bound, but if you want your relative error or your failure probability to be super low, at some point it's better to just give me a deterministic counter. Okay, so there's both an upper bound and a lower bound. And this was shown actually by myself and Hua Cheng Yu, and we just submitted it, so it'll probably be published in 2021, but we'll put it on archive shortly. Yeah, and I guess you saw the plot, so you saw the story, which is, we had this algorithm, we thought, oh, like, okay, our algorithm is not too complicated to implement, so we implemented it, and it gave exactly the same results as Morris empirically. And then we went back to Morris, and we said, you know what, probably people were not analyzing Morris the right way. And we went back to Morris, and we proved that, in fact, Morris does achieve this bound. But you don't get this bound just via, looking at the expectation and the variance. You have to do something a little more sophisticated to get this bound for Morris, but it's true. So that's all I have for you today. This is maybe one of the oldest streaming algorithms that was ever studied, counting, back from the late 70s. And then next week we're gonna look at some more problems as well and more techniques. So any questions in the last minute of class?
Oh, I just have a quick question about the previous part. So how did we get the bound on the variance to be n squared over 2? Oh
yeah, I didn't do the calculation.
Oh, I see.
I did do the calculation for the expectation.
Right.
So let's see. Let's flip through here. Where did I? Yeah. So I did do the calculation for the expectation. That was right over here. The calculation for the variance is very similar. It's some inductive proof. It's going to be in the notes. Okay, I just didn't want to take time in class to do it because it's just going to take more time, and it's not. You're not going to learn anything from it beyond what you saw from the expectation calculation.
Okay, I see.
And any other questions?
How long did it take you to make the discovery? The improvement in runtime thing.
Oh, not runtime. I mean in memory.
Oh yeah, and the memory thing. How long did you work on it?
It was a pretty short project. I mean, honestly, I think it's kind of funny because this problem has been around since the 70s. So why did it take until 2020 to improve it? I think the problem is people got comfortable. People just said, oh, there's this old algorithm from the 70s. We have a pretty good bound on it. And why wouldn't this bound be optimal? I think maybe people just never thought that it's not an optimal bound. In fact, we fell into that same trap, right? We also thought that the bound for Morris was optimal, which is why we tried to come up with a different algorithm. Only after we experimentally, tried to evaluate it did we realize that Morris itself already achieved this bound. And once we realized that, going from that to proving that Morris achieved the bound was a matter of days.
I see. So now you have a concrete proof that it's the lowest bound of memory you can achieve, right? So,
how do you prove that you can't do anything better?
Yeah. I'm not asking how do you actually prove it? I'm just saying there's a concrete proof, right?
There is a proof that not just Morris, but there is no algorithm that does better. There's no algorithm that does better than log n plus log 1 over epsilon plus log 1 over delta. That's a lower bound on the performance of any algorithm.
Sounds cool.
Is there a reason to think that it should be log 1 over delta instead of log 1 over delta?
That's a good question. And actually that goes back to maybe the previous student who asked the question, why didn't people try to improve it? I think the problem is, it was some kind of bias. Log 1 over delta is a very natural bound. It's the bound that you often get when you look at the dependence on failure probability. So I think when people saw that, hey, we have a bound of log 1 over delta, I already showed you basically why the other parts were right. I already showed you why log n plus log 1 over epsilon was kind of the expected answer, right? But I took the different powers of 1.01 that were separated 3 apart. That was basically that argument. So that part was already kind of clearly optimal. And then log 1 over delta is what people usually get for most problems. And it's usually optimal, okay? So I think that's why people didn't even bother trying to improve the bound. They just assumed, of course, it's optimal. Log 1 over delta is always the natural answer. But it turns out for this problem, it's not the right answer.
For the case of 2, you use the median of means. Can you also do that for the last algorithm? Does it make it better?
Well, it's already optimal, so you can't really make it better. You mean the Morris this changing the base of the exponential? So actually, let me go back. So if you're talking about this algorithm here, right? I mean, this is just the Morris counter, but instead of incrementing with probability 0.5 to the x, you increment with probability, like very close to what the 1 minus some small number to the x, 0.999 to the x, right? So that algorithm is already optimal, right? So there's nothing you can do to it to make it any better. It's already the best that it could possibly be. And also, it's like the reason that you're doing the median of means thing, first of all, why are you doing the means thing? You're doing the means thing to decrease the variance, right? But you have to take the mean of 1 over epsilon squared of them to decrease the variance. Or you have to take the mean of r of them to decrease the variance by a factor of r. And for this problem, that turns out to be very inefficient memory-wise. A better way to decrease the variance is just change the base of the exponential for this problem.
I have a question about the lower bound. So in what sense is it optimal? Because you mentioned that we can get better scaling with epsilon by just taking the deterministic counter, right? We get worse scaling at n. So like, how do we know we can't trade off, like get a better scaling in terms of epsilon, but like trade it off with a worse scaling and delta or something?
I mean, okay, so first of all, how do we know? We know because we have a mathematical proof. So so we know that you cannot beat this bound, but if you want me to be precise, the proof says that the optimal bound is the following thing. It's the min of log n and log n plus log 1 over epsilon plus log 1 over delta. So that's the optimal bound. No matter what epsilon, delta, and n are, that's the best you can do. The first term is achieved by a deterministic counter. The second term is achieved by the Morris algorithm, by the Morris counter. I'm not sure I answered your question.
Well, maybe to elaborate, is there an easy way to pick between these two on the fly? Like, can you implement an algorithm which kind of does as good as both of these?
Yeah, so the algorithm basically the very first line will be an if statement, right? So what does the algorithm get as input? The algorithm gets as input epsilon and delta. Well, actually, so that is a good point because if you don't know what n is ahead of time, then you don't know which one to pick. But if I promise you that, the final value of n will never be bigger than t, then, you can basically compute these bounds where you replace n with t and then pick the one that's better and then do that algorithm. So the first line of your code will be an if. If log t is smaller than the other thing, I'm just going to do a deterministic counter, else I'll do the Morris counter.
Could you also run both up until you get n and then discard the memory?
But then your memory is the sum of both, right?
Well, it's only up until n, right? Or I don't know.
Yeah, but I mean that's exactly what we're trying to avoid, right? I mean, if I'm using memory log n up until the end, then I'm using memory log n. I don't want to use memory log n. I want to use memory log n.
Yeah.
Did the analysis actually use the fact that we have some hypothetical upper bound on capital N?
So then the algorithm doesn't need to know that.
So then it's a little unsatisfactory to say the first step would be to check if epsilon and delta satisfy some condition depending on t, right?
That's right. Yeah.
Because the one that you just presented works for any without assumptions on an upper bound.
Yeah, that's right. So that's right. So if you wanted to actually achieve this upper bound, right now, maybe I have to think about it for a little bit. It's not clear to me that you can do it without having some kind of knowledge of an upper bound. It might be possible. It's not immediately obvious to me. Any final, okay, so I guess any more questions? I'm happy to answer questions. I see there are some in the chat too. Let me see what's going on in there. Okay, no, just, okay. So good. I guess I'll see you all on Monday then if there are no more questions. Okay, take care.
Thank you.